That was Shane Bieber. He pitches for the Cleveland Guardians, previously the Cleveland Indians. He went to, he was in Little League in Laguna Hills, along with my son, Cameron. And they both played All-Stars together. They played high school baseball together. Shane is 1 year older than my son. My son was lucky enough to crisscross with him for a few years on each of those. But anyway, we have watched Shane's trajectory through college and into the pros, and he, a kid from our high school, has won the Cy Young Award, has won the All-Star Game Most Valuable Player. He's only, I think he's 27 years old now. But anyway, it was Father's Day last Sunday, 2022. Indisputably the greatest day of the year. And we went up, along with a lot of other Laguna Hills people, to watch Shane pitch against the Dodgers. Now, I have never rooted against the Dodgers in my life. This was the first time. It'll be the last time unless Shane comes to pitch again. But anyway, he didn't get a decision in this. He went into the seventh inning. The Guardians ultimately won the game, but he didn't get the win because he wasn't winning when he left. So that's how the rules work. Anyway, I show you this type of stuff because at test time, I'm interested to know who's watching the videos. And there are people who attempt to go through my course and can be successful using just the notes that I've given and decide that they're going to forego watching the videos. Now, I try to put some important stuff in these videos that aren't necessarily in the notes, so I want you watching these videos. Well, one way I can verify who's doing it is to ask a question on the exam. So when I need 5 more points that I have to find somewhere and I want to give them to you basically for free, I will ask questions about these videos. And they'll be simple questions. All you needed to do was watch them. But in this particular case, a possible test question would be, Professor Bondy knows a famous celebrity or athlete, and his name is, A, B, C, or D, and one of those, of course, will be Shane Bieber. Maybe Justin Bieber will be in there. That will not be the right answer. Maybe Snoop Dogg, something like that. And, people who don't watch the videos would think, hey, Snoop's cool, Dirk's cool. I could see them hanging out together. Maybe they do. Maybe they watch each other's videos on the internet. Mutual admiration. So I can see a lot of people, circling that one if they're not watching the videos. But you will know that the right answer is Shane Bieber. So here we go. Welcome to lecture number 3. Now I'm going to do, let me back up. If you recall at the end of the last lecture, I said things can get complicated quickly, particularly when the applied loads would create a maximum moment at a different location than the maximum pre-stress moment will be, the maximum primary pre-stress moment. And that's the example I'm giving right here. I will also give you a homework assignment where the exact same thing happens. Most of the time, I haven't made up the homework assignments yet, so I'm still thinking about exactly what I'm going to do. But most of the time, I give you a parabolic profile and then some point loads. But the basic idea is the same. When the applied load moment is not at the same location as the pre-stressing maximum moment, the two maxima are not the same, then it creates a complication. So let's go through an example where that is the case. A 68-foot beam. Uniform load 2.1 kips per foot, and straight tendons, so harp tendons. Sometimes I will call those harp tendons. 42 inches deep. These are the section properties. You've got the notes. So we're going to try to find the maximum stress at the top and the bottom of the beam. They may or may not occur at the same location. We're going to use what I call the mathematical method, which is the tendons are in, we're accounting for the force times the eccentricity. That primary pre-stress moment, we're going to keep track of it, set up equations to tell us what it is at any point, at any value of x along here. Then we're going to do a second method and stand back and realize that the point of this is I'm trying to convince you of how valuable this equivalent load method is. So when you do your homework, you probably won't love the mathematical method. That's kind of the point. In fact, for those of you watching the videos, which you all are supposed to be, I would suggest doing your homework doing the equivalent load method first. That's going to be the easier method. It shows you, I think, clearly where the maxima are, and then you can go back to the mathematical method and do that. You can do anything you want, but that would be my recommendation. So here's the mathematical method, or the tendons are remaining in. So we need to know, and we're going to draw that tendon for some value, for any value of x, we're going to need to know what that force times eccentricity is. For any value of x, we're also going to have to determine an equation for the total load, or the applied load. Now, as I've said a number of times now, we are going to shift this tension load, or this compression load, the compression load that is also happening here, gets moved up, and we will apply an offsetting equivalent moment to make up for the statics that we kind of messed up when we did that. Now if we look at this beam under 2.1 kips per foot, we will get 71.4 kips of reaction at the left. So you don't need me to do that for you. So here's the setup, and here's the cut. This cut is somewhere less than 40 feet. It's less than the low point of the harp. It will go up to and include that. You in your homework will set up equations for the stress. We will assume, just writing these equations, that the stress is going to be tension on the bottom. The numbers will shake that out if that's not the case, but we'll write the equations as if that is the case. So as I also have said before, we're always talking about negative F over A. The stress, compressive stress in our course is always considered to be negative. If we're assuming that tension is on the bottom of the beam, that tensile stress will be due to the applied loads, the total load moment divided by the section modulus on the bottom. And the stress on the bottom of the beam due to the pre-stressing will be the primary pre-stress moment. Gotta get in there. F times Z, primary pre-stress moment. So that would create tension on the top or compression on the bottom. Since we're looking at the bottom, that's going to be the compression. So, working this way through a little further, we're negative 347 psi in compression, and we'll combine these to be total load minus the primary pre-stress load divided by the section modulus. Now in this equation, for the stress at the bottom, this equation maximizes when this term, the MTL, total load moment minus the primary pre-stress moment, is a maximum. So that's what we're going to look for mathematically. So we need to write first the total load moment, applied load moment in terms of x. So that was the reaction times x minus the 2.1 kips per foot divided by 12 times x squared over 2. And that gives us this equation, which is the equation for the moment anywhere between 0 and up to 40. Now we're going to look at the eccentricity. Well, the eccentricity at x equals 0 is 0. At x equals 480 inches, the eccentricity in the beam is 25.25 inches. That's what we're calculating. And remember, the beam we started with is here. So we have an equation for the eccentricity itself, also in terms of x. Now, we'll put these terms together. The applied load moment minus the primary pre-stress moment, and create a single equation. So that's representing basically the two moments working against each other. The derivative of that equation will tell us where we have a maxima. Now, we may also have a maxima at 40 feet, so we'll have to check that independently. In fact, I'm asking you oftentimes in the homework to check the two boundaries. Wherever the two ends of this equation apply, if you remember calculus, you actually have to plug those two values of x's in also to see if they happen to be a maxima. All we're doing is creating, some type of moment that, and we're checking the tangent of that moment. If that tangent is 0, then as you remember, we have a maxima, but you could have a maxima at each end that doesn't have the tangent being 0. Good old calculus. So by the way, I call my kids friends, the ones who've been successful, like Shane, and my son also has an airline pilot friend who's flying major jets now. So I consider them my friends now too, and I introduce these people as my friend, and it makes my kids insane. They roll their eyes. It's part of the dad joke stuff that we parents like to do. But yeah, so if the successful kids' friends of my kids' friends, become my friends too. But the loser kids, no, they're not. I never introduce them as my friend too. I'm sure you love it when your parents are introducing your friends as their friends, if you're anything like my kids. Okay. Back to the game. We take the derivative of that equation, and we get this. Set that equal to 0. We have an x value of 272.7 inches. That's hopefully, if we've done everything correctly, that's where a maxima is occurring due to the applied load moment and the primary pre-stress moment going the other way. So with that value of x, I go back to the equations I'd already established and plug in the x values and get a total load moment. I go back to my eccentricity equation, plug in that same value of x, and get an eccentricity at that location. With all that information, I can go back to that stress equation, check the stress at the bottom of the beam. I plug everything in, total load, primary pre-stress load, and I get a maximum tensile stress at x equals 272.7 inches from the left of 0.579 KSI. So the stress at the top of the beam, remember that's what the question asked for, you are trying to find the maximum compressive stress and the maximum tensile stress, wherever they occur in this beam. Now, maybe they occur at the same location, maybe they don't. I would bank on the second, the latter. So the stress at the top of the beam, this is always negative F over A. We're going to put a negative in front of this term. So whereas this was positive here, we're going to reverse it. We know that this total load moment minus the primary pre-stress moment, if it was creating tension on the bottom, it's creating compression on the top. So that negative turns this whole thing into compression. And at the top of the beam, we calculate having a compressive stress of 750 psi. Negative says compression. So we need to check at the boundaries also, but that's what you need to do. I'm telling you that that doesn't govern in my particular example. So I could go back in, and I should go back in, plug in the value of x equals 40 feet or 480 inches, and do that calculation. We're going to actually see when we do the equivalent load method that that's not a maximum, but you should be doing that. I take the lazy way out in a lot of these examples in the interest of time, of course. So not too bad, but we had to use some math, not high-level calculus, but we had to do some. It's kind of fun. And we got the two values. Let's see what T.Y. Lin says about doing this. So we go back to just looking at the tendon slope. These are the forces, these black ones, these dark ones are the ones keeping this tendon in its shape. The equal and opposite, dashed, are acting on the concrete. So it's easier to see the forces, in my opinion, on the tendon, so I draw it that way. But then I remember that I actually care more, if I'm calculating stresses in concrete, I need the equal and opposite of those. So taking small angle theory and those angles, I can calculate, knowing that there's 450 kips of tension in that tendon going through this angular change, tells me that there's an equivalent load, not a real load, this load's not there, but we are going to calculate an equivalent load of 57.49 kips. And now we're going to take the tendon out, we're going to put that load in. We can put these in too. They don't actually come into play because that's on a support, but they're there. So, in fact, I did draw those. Good for me. So now I'm just putting all the loads on the concrete only. And this is extremely important that you write concrete only. I write concrete only. This is just what is happening to the concrete. This is not going to be statically correct for this beam. But what you're going to see is what's going to be correct is the stress calculation. That's all we're caring about right now. We always care about statics, but we understand that what we are doing has eliminated, statically this load should be there, and that should be offsetting this so that they don't occur. Remember, there's the upward version of this right up here. So these would all cancel out to be statically correct. But if we only look at what's happening to the concrete, and this gets to be a tough concept, I understand. If we just look at what's happening to the concrete and we take all these other tendon equivalent loads and just leave them hanging off to the side. We know they're there, but we have separated the tendon from the concrete, and we've replaced on the concrete the tendon with an equivalent load that's not really there. What happens when we do that? Now all of a sudden our life gets to be pretty easy. We're no longer, in the first part I just said limit all your calculations to 0 to 40. You can make the assumption that the maxima didn't occur on this side. So we're already excluding part of the beam from the analysis. But we didn't absolutely know that, and sometimes, the maximum might be on the other side. But so I made life a little bit easier, and I'm going to help you most of the time in the homework also just focus on a section of the beam where I will tell you the maxima occurs, so you don't have to do too much work. But when we're back to looking at loads, we don't really have to look at pieces and sections, and I don't have to tell you where the maximum is going to be. We can just look at the whole thing. It's just as easy. So now we calculate a concrete-only shear diagram, a concrete-only reaction that is not a reaction, and that's a big deal to me. It's a big deal to me that you understand what a true reaction is. A true reaction, to this point in the course, means that it is due to applied loads and applied loads only. All of the equivalent loads will cancel each other when you put everything in the pool. When you throw everything in, the equivalent loads cancel each other. So there isn't a reaction due to equivalent loads. There can't be. And that's part of your homework assignments, that you're going to tell me that you understand that too. So when we come up, remember, this was the static reaction. That we already calculated. This, in the concrete only, is telling you that that's what the reaction, at least the concrete thinks that's what the reaction is. Not statically correct. This is statically correct. This is not correct. But we're doing all this incorrect stuff because we get the right stress answer. And we needed an easy way to do it. And thanks to T. Lewin Lin, we have one. So I take this incorrect reaction, draw the shear diagram, draw that point load going up, bring that load at 2.1 kips per foot over to here. There's another reaction that the concrete thinks is happening of 37.56 kips. That's also not statically correct. This is the statically correct reaction. And now I'll create the moment diagram from the shear diagram. So the area under the shear diagram is equal to the change in moment between those 2 points. Be careful about that when we go into indeterminate structures, multi-span beams. It's the change. It's not the absolute moment. It's the change in moment from here to here. So it just so happens we started with a 0 moment there. So the area under this shear diagram will be that moment, but only because we started at 0. If I give you a negative moment that goes like this, all bets are off. So we calculate the concrete only moment diagram. Now in your homework, I'm going to have you also make sure you show me what the statically correct moment diagram is. Statically correct moment diagram will be only due to applied loads. Or, in other words, it's due to applied loads plus the equivalent tendon loads plus the equivalent concrete loads. Now, if you want to think about it that way, that's fine, but the last two canceled each other out. So all you're ever left with is the applied loads. That's the statically correct shear and moment diagram. This is not statically correct, but it sure is going to be useful to us. So now I told you that the maxima was going to occur at inside the 0 to 40 foot range, and that's exactly what happened. This is the location that you calculated mathematically that had a 0 slope to the tangent. Doing a quick count. And this is the 272 point, was that 4? What did we calculate before? 272.7. Okay, close enough for government work. Anyway, the equivalent load method and that mathematical method both told us that we have a maxima here. It's just this is a lot easier to see. What I can also see is that this is not a maxima, and neither is this. So I get the full picture, and it was, in my opinion, a lot easier. Now you guys are in school, your brains are really sharp, firing on all pistons. all cylinders. You probably aren't bothered by doing math. When you get to be, in your 50s, 40s, 60s, you're going to want to go back to the shear and moment diagrams. There's all the math you need is packed into these. But if we can just start with loads, get reactions, get a shear diagram, get a moment diagram, we're pretty happy. Pretty happy as old men and old women doing that. So from that moment diagram, I'm going to calculate the stress again. I'm going to calculate the stress just like I did before at the bottom of the beam. M over S minus F over A. You can put the minus F over A in front if you like, or not. Just needs to go in there with a negative sign in front of it. So now we have that concrete-only moment, that 542.9 foot kips. Convert that to inch kips, divide by the section modulus, and subtract the direct compression. And lo and behold, we get exactly that same 579 psi in tension at the bottom of the beam. At the top of the beam, we just reverse that sign. And remember that we're calculating to the top section modulus. Minus F over A. Plug those numbers in, and again, magically, come up with exactly the same 750 psi in compression at the top of the beam. Now, you being young people, all very good at math, may think, I can do either one of those methods. That's fine. I am here to say I think that the equivalent load method, dramatically easier, a lot clearer, and I will tell you as somebody who grades your homework assignments that a lot of mistakes get made in the mathematical part of this. That's why I encourage you to send those to me over the weekend and let me review it. A lot fewer mistakes happen doing it, the engineering approach, the way we like to. Convert it to a load, calculate a fictitious reaction, shear diagram, a moment diagram, but from that moment diagram, get exactly the same answer. So, that was all great, and that last example was a simply supported beam, which never happens. In reality, cast-in-place concrete wouldn't make much sense if it was always statically determinate, simply supported. What makes concrete fantastic is its natural indeterminacy, its natural multi-span. It's just as easy to pour concrete in forms as indeterminate multi-span systems as it is to place them. It's easier, actually, than trying to place them as statically determinate bay by bay, like a steel beam being placed or a wood beam being placed or a precast concrete beam being placed. So we're going to be very interested very quickly in indeterminate multi-span systems. Now, hopefully the last example already was enough to convince you that the equivalent load method is already superior, but this ought to really slam the door shut if you're thinking that you like the math way. So let's look at what happens if that member is statically indeterminate. Well, I'll take the same beam, since we've been working with it and we've already know what the primary pre-stress moment is. That keep going back to that same well. But I'll take that same problem and I'm going to add an interior support at midspan. So now I have an indeterminate system. I have a two-span system instead of a single-span system. What happens? Well, something entirely new and different gets introduced, and I don't like introducing that necessarily at this point because it's a major part of post-tension concrete design later in the course. So I'm going to touch on it, hopefully not confuse you too much, but I have to mention it now or I can't fully sell you on the beauty and wonderment of the equivalent load method for all cases, statically determinate and statically indeterminate. So I'm forcing this to be statically indeterminate. And I'm saying that before I put that support in, I can calculate stresses using the equivalent loads, and I can also calculate deflections using equivalent loads. Those are the only two things of value that you get using this equivalent load method, but they're extremely powerful. I mean, that's extremely important to know. It's the concrete itself that has the stiffness. The tendons aren't considered to have any stiffness. So the only thing that's deflecting is the concrete. And once again, if we just look at what the concrete thinks is happening, we can calculate deflections based upon just that. And that will be the deflection of the beam. So without that support, this beam wants to deflect up 5 WL to the fourth over 384 EI. Go to your steel manual if you're not believing that, but that's what a simply supported beam under an equivalent load wants to deflect at midspan. That's the maximum deflection. So we've actually calculated what the equivalent load is, 550 pounds per foot, 0.55 kips per foot. So I can calculate, and I'm going to leave everything in terms of feet and EI, what the deflection at the midspan is, or wants to be, without that support. But here's the thing. As soon as I introduce that support, it can't happen. Now there are two things in post-tension concrete that are completely different in every way, shape, and form than any other material. The first is the concept of equivalent loads to calculate stresses and deflections if we want. The second extremely important point that doesn't exist anywhere else in any other material is this concept of secondary reactions. And that's actually what is happening here. This beam wants to move up, and this support is holding it down. That creates a real reaction. That is not a fictitious reaction. That's not a reaction, an equivalent type of reaction. It is a statically correct reaction. And it's very real and very important, and it's going to show up later in the course. So I'm introducing it just to confuse the heck out of you, and then we're going to leave it alone for now. But it's part of this particular point I'm trying to make. So right at midspan, there is a reaction holding this down. That point load reaction must be equal. If that support is there and that support is not moving, that deflection due to that equivalent load must be exactly equal to the deflection that the beam wanted to go up. Remember, it wanted to go up this much, but there's a reaction holding it down. That reaction, we don't know yet, but we do know that the deflection due to that reaction going down must exactly equal what the beam wanted to camber up. So I can, again, using my trusty steel manual, I know that the deflection due to a point load at midspan is PL cubed over 48 EI. Love the steel manual. I set that equal to the deflection that beam wanted to go up due to the equivalent loads, and I calculate a reaction. I calculate what that reaction must be. In this particular example, it's 13.75 kips are generated by that beam being restrained from moving up just due to the pre-stressing. Remember, none of this has any applied loads to it in this particular example that I'm doing. This is just due to pre-stressing. I will back up one more time. Due to pre-stressing alone, this beam wanted to camber up. It's held down. That force holding it down is called a secondary reaction, and it's 13.75 kips. By the way, there are also secondary reactions here and here. These have to sum to zero because statics is our best friend. Okay. So there's actually a secondary moment. If these reactions are acting on the beam, I can actually create the moment diagram. There is a moment diagram. There's a shear diagram, a secondary shear, and a secondary moment diagram being generated by those support reactions, those support restraints. Sorry, I'm going to back up. So a point load at midspan of the beam, that point load at midspan of the beam creates a secondary moment. We're going to dive into this later, and this is probably confusing because I'm just throwing it at you, but we're going to go through it slower later. It's an extremely important part of the strength design of pre-stressed concrete beams. But for right now, we're just kind of looking at the statics of this. What would it take to do that mathematical approach? So remember, in the mathematical approach, I'm taking F times E. But there's a new component if it's statically indeterminate. And this is really important. You may want to listen to this more than once. You may want to listen to this again before the exam. But whenever we put the equivalent loads on a statically determinate member and get that moment diagram will be F times E at every location. However, if the beam is indeterminate, that won't be the case. We'll put the equivalent loads on, which is exactly what we just did. We put the equivalent loads on in this example, and we're not going to get F times E at every location because of that restraint force. That restraint force created a new moment diagram called the secondary moment diagram. Again, we'll get way into this later. By the way, I'm sorry if you're scrambling and writing, I should have told you this. I want you just to sit back and watch this. This is not something I'm testing you on the first exam. I'm just doing an example here that I want you to sit back and really think about. I'm not going to test you on anything I'm doing right here. It's not part of any of your homework assignments. So it's more important that you just sit back and take this in. So we have a primary pre-stress moment diagram, F times E. We have a secondary moment diagram. And those combine to be a final moment diagram. Now that's a lot of work, and that's only two-span beam. A two-span beam, we had to figure out the reaction, set the displacements equal to each other, have compatible displacements. Okay, in a two-span beam, that's not so bad. 6 spans, impossible. I mean, basically, you gotta really get into a good computer doing all that work for you. So far, I can, with a two-span beam, with each span being equal and my steel manual, I can get through this, kind of by hand, so to speak. So I end up with a final pre-stress moment diagram. But I had to calculate that deflection, I had to calculate that point load, that secondary effect. Here's the beauty, and this is, put pencils down, just watch and understand this. So remember, we had actually calculated earlier that pre-stressing equivalent load due to the parabolic profile was 550 pounds per foot. So I'm just putting that on the beam. I forget everything we just did. Simply walk up to that beam and put in on the two-span beam, equal spans, put on 550 kips per foot, or pounds per foot, 0.55 kips per foot. Again, using my trusty steel manual, as I say right there, I will get, it tells me what the maximum positive moments are, or positive span moments are, and what the support moment is. Lo and behold, nothing up my sleeve. I got the same exact thing. All I had to do was pull my steel manual out, or just do a simple moment distribution on 2 spans. The point of all this, and I hope pencils are down and you're just watching and listening, the equivalent load method applies equally to statically determinate and statically indeterminate members. Doesn't matter if this is 2 spans, 1 span, 6 spans. If I can calculate the equivalent loads to the tendon profile, just simply place them on the beam regardless of how many spans it is, I will get the final pre-stress moment diagram. That's what is so powerful. If everything we've been doing up until this point was only for statically determinate members, it would be useless. But we are going to be able to take this concept of using the equivalent loads on anything, on any span beam. It's going to be just another load case, just like the dead load, just like the live load. We will have a pre-stressing equivalent load case, and we will jump straight to the final pre-stress moment diagram. We didn't have to calculate the deflection of the beam as if there were no interior supports, what the reaction would be to offset that deflection. All those complications disappear. We go straight to the final answer with the equivalent load method. That's the beauty of it. That's the power of it. And if you weren't a big fan before, I can't imagine you not being a big fan now. And when I've said previously that pre-stressed concrete was theoretically possible and practically impossible before T.Y. Link came up with the equivalent load method, I'm telling the truth. It really, nobody was doing it. It was just an academic fun exercise. Now it's brought to the masses. Now anybody can calculate. As long as you can calculate the equivalent load, you can get straight to the final pre-stress moment diagram. Remember that in an indeterminate system, this is not F times E. It's 2 components. It's the primary pre-stress moment diagram plus the secondary moment diagram. But the equivalent loads, just putting those on, take you straight to the end. Later in the course, we're going to have to actually work backwards, and we're going to want to pull out those secondary effects. But not now. ACI has permissible stresses in the concrete flexural members. Now you should look at this. You should look at your ACI. They keep changing locations on me, but there's something in there. If you do go through the code, there's something called transfer stresses. Transfer stresses are stresses that are happening immediately as the concrete is, or the pre-stressing steel is being pre-stressed. And so it's the transfer stresses in the concrete that become critical at that time. We are not, in this course, going to worry about that. And I will tell you, after doing this for, I don't know how long I've been doing this, since 1989, that's never, ever controlled a design. These transfer stresses, something will only go wrong stress-wise if you have a bad design, to be very honest with you. In reality, we should be in complete compression at the time of transfer. At the time of transfer, the sections, the entire floor is formed and being supported. It is being shored, so it's not really bending or doing anything just yet. So these really are not going to come into play for us. We go to service stresses. Service being every day, not being LRFD, not being load factored, no fee factors, just the actual loads that we really expect day in, day out to have on this structure, or we allow that much. You have two choices in the code, Class U and Class T. Class U means uncracked. Uncracked concrete, theoretically, very good. That's going to be what we focus on. T means transition. Means we're transitioning from uncracked to cracked concrete. It's important to note right here that the code allows pre-stressed concrete to crack. It actually is right there. It's in that transition period. In fact, there's even another case that I'm not going to talk about that lets it crack even more. But I don't want you leaving my class being one of the people who run out and say that pre-stressed concrete can never crack. It will crack for other reasons that are beyond your control, largely the contractor when they choose to place the concrete, what kind of weather conditions there are, how well the forms get oiled. It goes on and on. How long they wait to stress. You can start developing shrinkage cracking before stressing ever occurs. So there's a lot of things outside your control, but these are the theoretical numbers. This is what numerically, if everything else goes perfectly, we would have uncracked concrete. But you can't ever promise that. So in this Class U and Class T section, you can see that you have two choices for the extreme fiber in compression, 0.45 F prime C. We're not going to use that. That's just due to pre-stress and sustained load. That's one load case. And I will also tell you that in practice, nobody cares about any of the compressive stresses. We care about it. But again, you've got to have a terrible design before. Concrete loves to be in compression. So it's happy, very happy being in compression. It is very difficult and only the result of some type of terrible design that you will ever, just due to having pre-stressed concrete, exceed concrete allowable compressive stress. So we're in academic world. We're in the academic world. We are going to focus on this. I will ask you to make sure that your extreme fiber in compression due to all loads, dead plus live and pre-stress, do not exceed 0.6 F prime C. This is the only one we're using for compression in our class. This is in the code. I presented it, but we're not using that one. So everything we're doing, 0.6 F prime C. When I ask you what the compressive stress is compared to the allowable compressive stress, 0.6 F prime C is the allowable compressive stress. Also, if you are reading your code, you have uncracked tensile forces, tensile stresses, transition tensile stresses, and you'll also note that two-way slabs have a different allowable tensile stress. The one that we are using in this class, all that you need to be responsible for is the uncracked Class U 7.5 square root F prime C. So whenever, on exams, on homework assignments, at any time, project during this course, I ask you to verify that the allowable compressive stresses have not been exceeded and the allowable tensile stresses have not been exceeded. These are the two that you need to be concerned about. Nothing else on this page do you need to be concerned about. Okay. End of lecture 3.